So good morning, the only brave soul who is still listening my monologue lectures. Now we're facing lecture 6.6, where I will be speaking more about the total internal reflection. So as in the previous lecture, we noticed that at a specific critical angle, when we were coming from an optically more dense material into optically less dense material, we had an example of glass-air interface. So when the angle of incidence exceeds a critical angle, all light is actually being reflected and no light is anymore transmitted through the interface. And this process is known as the total internal reflection, and I will be now speaking more about this phenomena in this lecture. So I will derive the equations for the critical angle theta c, at which this total internal reflection, usually abbreviated as TIR, starts occurring. And I will mention a few example applications where total internal reflection is being utilized. And I will point out that even though no light is being, or no propagating field seems to exist anymore in the air, in the optically less dense medium, there actually will be an evanescent field, not a propagating one, that still exists above the interface. And finally, at the end of the lecture, I will point out that the fact that we have an evanescent field, we can also have a phenomenon known as a frustrated total internal reflection. And I will end the lecture by introducing this and speaking a little bit about its meaning and importance in terms of real life applications. So this is what I will be speaking about during this lecture. So we have discovered in the previous lecture that when light arrives to the interface, that where the first medium from which it arrives is an optically more dense medium, all light can be reflected. And this figure explains essentially the scenario. So I have my Ki, the wave vector of the incident wave, and it's coming from the optically more dense medium, so from the bluer medium here. And now the indices are such that since I'm actually coming with the ray from here, the refractive index of this medium, the lower medium is Ni, and here the refractive index of the upper medium is now Nt. So please note the difference now in terms of the refractive indices here. And similarly, the angles are defined accordingly. And here, essentially, since I'm coming to an optically less dense medium, now the refracted ray does not anymore tend towards or bend towards the surface normal N here, but rather opposite. So towards more into the surface along the interface. And I can see that at the specific angle, this refracted ray can actually start propagating along the surface. And this is, in fact, physically how we can understand that the theta I would be corresponding to the critical angle theta c. So that would be the scenario when we are exactly at the critical angle. And of course, we can understand everything of this process, of this phenomena, by just looking at the Snell's law. So Snell's law was that we had the Ni times sine of theta I equals Nt times sine of theta t, or here the opposite, so that this is the Snell's law. And this, we just now look, and since the theta t here could in this case, that we're actually coming from glass into the air interface, that sine theta t would be larger than unity. And this condition is something that we cannot really fulfill this when we are using real valued transmission angles of theta t. And this is the trouble that we are facing here. So then essentially the critical angle will be reached when theta t equals 90 degrees. And this gives me a condition straight on with the Snell's law that the sine of theta t, the critical angle, is Nt divided by Ni. So essentially I'm plugging in theta t equals 90 into here, so I get unity out of here, and then I'm left with the sine theta I. I equate theta I with the theta c, and then I divide the left-hand side with the Ni, and this is how I get my equation for the critical angle. Very simple derivation. And now, let's simplify calculation of the Fresnel coefficient, because we want to more quantitatively understand what happens for the field. So we should really solve for the Fresnel coefficients. We can transform the above sine term, sine theta t, that this is essentially Ni divided by Nt times sine of theta I. So this is essentially just application of the Snell's law, and we will plug this into the Fresnel coefficient and do some other simplifications, and hopefully we will get some kind of more cleaner math out. So we transform this into a cosine. So the cosine theta t is essentially plus minus 1 minus sine squared of theta t and a square root of this. So this is equal to plus minus I, imaginary unit, times sine squared theta t minus 1 and square root of this. So we essentially transform this into a cosine, and then we progress. And now we want to look at the Fresnel coefficient. So let's look just for simplicity case, the Fresnel coefficient for the case that the incident field is perpendicular to the plane of incidence. So please note the sublabel indexing here. Perpendicular symbol here meaning that the electric field is perpendicular to the plane of incidence. And we can now calculate this Fresnel coefficient for reflection. So this R was and is given by Ni times cosine theta I minus Nt times cosine theta t, and similar kind of terms in the denominator. And then we plug in what we have just now discovered for the cosine of theta t, and we have a terms that look something like this now here. And then similarly in the denominator, but now minus plus signs, and we have an imaginary unit times something here in here. It looks formidable, but don't worry, these terms actually are identical. So in fact, this is actually quite good in terms of math, because now we can just say that these things are actually complex conjugates of each other, these two terms here. So that the numerator and denominator, they're actually whatever numbers they are complex conjugates of each other. And this is super nice, because now we know right away that if we want to calculate the reflectance, the capital R, and capital R for this given polarization, please note that the notation transfers also to the transmissivity and reflectance in terms of polarization, so that this is defined as the modulus square of the R. And now, since I'm taking a modulus square and of a ratio of two complex conjugate numbers, I know right away that the length will be unity. If this doesn't click right away how this is the case, please think of a complex number graphically, so that you would draw an arrow at the complex plane, so that the x-axis would be your real axis and the y-axis would be your imaginary axis. And what is a definition of a complex conjugate of a complex number is that essentially you will just flip the number, the vector here, with respect to the y-axis, and the length is not being modified, so that you know that when you are now calculating the length, the complex conjugation doesn't do anything to change the length of your complex number. Now we have essentially derived an equation for the reflectance, so capital R, and we know that that will be unity. And of course, this is what directly implies to us that all of the specific polarization of light is being reflected. And this is of course quite obvious from the case of point of view that we started by looking into total internal reflection, and we already knew that all light will be reflected. But at least this is now like verifying the case that even the Fresnel coefficients change accordingly. And we can repeat the calculation for the other polarization component too, so that also the polarization component where the field is oscillating parallel to with respect to the plane of incidence. So in the plane of incidence, we will see the same kind of result. So that of course, the total internal reflection also is being present in the Fresnel coefficients. But this is not the whole truth, and more on that later. But first, I will speak a little bit about some kind of applications of total internal reflection, often abbreviated as a TIR. And this is actually a process, a phenomena, I should say, that is being utilized in many applications. So for example, if you think of optical communication fibers, and we're looking at internet, using internet every day, and right now you're watching things from YouTube, so that we know that information is being carried in huge amounts across the globe somehow. And most of this communication, transferring of zeros and ones, is being done by optical fibers. So that's the kind of core framework forming the way how optical communications works, or communications works nowadays in globe. And optical fibers, they are an example case of a waveguide. They essentially are based on the fact that you have a core layer or core material in your fiber, and that has a refractive index higher than the surrounding layer, and then total internal reflection will trap light to be transmitted only through the core and not the other layers. And this is the kind of physics that allows people to make optical fibers, and that's it. And then they are being utilized everywhere nowadays in our modern society, especially in terms of optical communications. Waveguides, they are basically the same thing as optical fiber, but now done slightly differently. And there, the idea with waveguides is not to transmit light to distances of several kilometers, but rather of the order of some centimeters. So that essentially the idea of using waveguides is that we can make optical circuits and photonic integrated circuits, so that how we can make photonic components and devices, instrumentation that is more on the chip scale and not based on free space propagating optical components. So this is a difference. For example, if you want to do spectroscopy, you want to use a spectrometer to actually measure what kind of different frequency components of light are, for example, transmitted through your sample. And the main thing here is that you need an instrument known as a spectrometer. And many of the times, let's say spectrometers are quite bulky devices. So even though they can be handheld devices, like they are not of the size of a few millimeters in size. But if you take use of photonic integrated circuits and do things based on waveguides, you can actually make a spectrometer which fits, for example, inside a small coin. And then you can fabricate things quite easily, and you can in fact even fabricate thousands of these kind of spectrometers into a single optical wafer made, for example, out of silicon or other waveguiding materials. And you can make very cheap spectrometers, and you can make them fast, so that that's the kind of the potential and the interest in photonic integrated circuits, so that you can make really things on a massive scale, you can make them cheap, and you can make them on a small scale, which often implies that they are also more energy efficient than bulky devices. And of course, this is very important for the future of emergence of green technologies. In optics and photonics, we're really interested in trying to make more energy efficient devices. And we think that that's the future, that they can replace more energy costly electronic devices with optical devices. And this is really a big trend currently in our field. Some other examples, reflecting prisms, and that may not say much to you, but if you know binoculars, those devices that you can use and look to the distant objects, and they are being highly magnified. Most of the time, the configurations that are being used to make binoculars, they are based on reflecting prisms. And prisms, of course, they can be used to change image formation processes. But in the case of these kind of components, you can actually take use of total internal reflection. So binoculars would be a kind of very good example. Fresnel ROMs, this sounds maybe not familiar to you, but it's an optical component. I think I will be asking you in a homework assignment about these, how they behave, because there's actually lots of good mathematics that we are then forced to deal with. But Fresnel ROMs are essentially components that allow us to change polarization state of incident light. And here we have been playing around with these two polarization states, whether or not the incident field has been parallel to the plane of incidence or perpendicular. So in a way, Fresnel ROM would be a one example component that we could use to adjust these between these two different polarization states or other states in between. So that would be another example case of a application. And there's plenty of more other examples regarding total internal reflection, but this is just a few examples. You can actually see total internal reflection taking place in many of like real life situations if you just pay attention and keep your eyes open. So that this is actually very often encountered phenomena. The interesting thing here, and we can see it shortly, is that even though all light is being reflected, this doesn't actually mean that the Fresnel's transmission coefficients will vanish. So even though the modulo square of the reflection coefficient is unity, that doesn't yet mean that the transmission coefficient would be 0. And this is super strange in first thought, because it doesn't seem to make any sense. But let's look into the math and see that in fact it does make sense in a similar way as Luke is Darth Vader's son. In a way, spoiler alert, sorry about that. But this is actually not impossible at all. Like Luke said in the beginning, that's impossible. I am not your son. But yeah, okay. A classical movie scenario. But let's consider what happens in the case of transmitted light in this geometry we earlier considered and we were shown in the figure. So we have the wave vector kt describing the wave vector of the transmitted light, and this is of the form that we have the amplitude of the wave vector kt, scalar quantity, and then we have the vector part, so we have the sine theta portion into the direction of x, so that the x hat is the unit vector along x, and then we have a component along the z, so that would be the z hat, the unit vector along z direction, and cosine theta t there. So this is how I can write my transmitted wave vector. And from here, essentially, my field is position-dependent field. I could calculate how it would look like. And applying the Snell's law, I could write it in a way that I have I'm applying Snell's law later on. So I have this plane wave component propagating along the direction of k. So this is just a simple math for a plane wave propagating along the direction of k. And now I'm plugging in this kt, and I want to look how this kind of plane wave quantity looks like when it's propagating along the direction of r. So basically in the direction where it's heading. So I insert the above into this equation, and I have this. So that sorry, I'm also making the replacement that I'm having r here, position vector x, y, z. So I'm replacing r here with the x and z's here. And I can take the different terms out from each other, and then I can apply the Snell's law. And what I have left is that I have something like this. So it looks pretty bad, but there's nothing new. I'm just taking use of what we already discovered. So I'm inserting here the form for the cosine theta a few slides earlier, and this is what I get out. And now the interesting thing here is that this guy, I have the imaginary unit here. So it's telling me that there's a field propagating along the x direction here, so that it still looks like a plane wave term. But then I have this kind of modifier, a multiplier, and I don't have the imaginary unit in here because I had the complex valued number I inserted here. So instead I have minus plus here. So essentially I'm actually having something that is exponentially decaying with respect to the z coordinate. And please note the z coordinate is defined that is the direction parallel to the surface normal, so that the kind of further I go from the interface, this term actually goes higher, so that the more the field is being vanishing. So let me repeat, the equation we just discovered was of this form, and basically it just tells us physically when we look into the math that we have a surface field, so that we have a component that propagates along the surface x direction, and that it's not being decaying, so in a way that looks like a perfectly normal propagating field, but that is multiplied with a component that is exponentially decaying along the z direction. So essentially, energy is not being transferred along that z direction anymore, but rather is a decaying evanescent field. And this is actually the kind of thing that happens when we have total internal reflection, so that we have a propagation field here at the critical angle. But on top of that, we also have a field that is not propagating along the z direction, but rather a evanescent field here. And that's the terminology here. When we have a field, but it's not propagating, but rather it's decaying, we say that it's an evanescent field. But it's a field, nevertheless. And this means that if something actually happens, so that we don't have a pure air anymore as our above medium, then something actually can happen. And what that other medium could be, for example, it could be a small scatterer. So only a small nanometer-sized grain of dust would be enough as acting as such a medium. So that if I would place a small dust particle, for example, here, it would be the case that the evanescent field might actually be coupled into this particle, and then I would actually have scattered light in here, and that would mean that there would be actually losses, and not all of light would be totally internally reflected at the interface. And this is actually hugely important in terms of practical applications when we are using total internal reflection. So because this gives us a loss mechanism in practice. So let's now look what happens and what are the kind of requirements that this would happen. Let's look at the third medium and consider that it has a refractive index of N3. And if this N3 is large enough, then an evanescent field can in fact take place in this medium, and it can be present in this medium, and more importantly, it can turn into a propagating wave. And then this propagating wave would be described with a wave vector K3, as will be shown in this figure. And this is that can actually schematically happen, and this phenomena would be called frustrated total internal reflection. So essentially now, if I would not have this third medium, total internal reflection would take place and all of light would be reflected into this direction. But now I'm placing a third medium nearby this interface, and if the refractive index profile is right, then this decaying field can actually start looking like a propagating field in here, and it can start propagating in a given direction. And this process is known as a frustrated total internal reflection. So even though there's no propagating field in this medium labeled with N2, there will be an evanescent field, and this evanescent field can actually manifest itself in the third medium, and then there can be a propagating wave here. And this is hugely important because this is the kind of practical loss mechanism that degrades the performance of typical optical instrumentation. For example, the optical fibers, waveguides, and these components. So this is what I wanted to say. And let me just repeat my example by just applying this, what we have learned of frustrated total internal reflection, to a case of an optical fiber. Or maybe I should consider a waveguide as an example, so that I do not even need to consider some kind of protecting cladding layers in terms of practical application. So I have my waveguiding material here, and it behaves as a waveguide, so light is being confined into this region. It's a small scale device, so let's say the typical dimensions of waveguides are of the order of some hundreds of nanometers or some microns. So I'm really speaking of a component which has the size smaller than a human hair. And then I have a macroscopic wafer-sized object where I have my waveguides placed, and they work ideally. And then actually I'm using them in a kind of normal operating conditions and not in a clean room. And I have dust particles flying around all over the place. And some of these dust particles that are also of the order of some microns will be nearby the waveguides. Or it can even be the fact that a human hair will be nearby the waveguide. And due to this fact, this piece of a dust, some dirt, or the human hair can actually start acting as this third medium nearby the waveguide, and that starts giving me losses. And this is a loss mechanism that very often takes place in waveguides. So this is the trouble. And of course, the usual solution into this trouble, that of course you protect the waveguide structure so that you will evaporate some kind of protecting material on top of them, so that the grains of dust that will eventually be hitting your device will not actually be close to the waveguiding layer, but rather they will be high above, because you have a protecting layer here, so that you essentially introduce on purpose a N2 material here, a second material that still makes it possible that the waveguide acts as a waveguide, but it makes it very hard that you would have a third material here, giving rise to a possibility of having frustrated total internal reflection. So this was my example. Hopefully that helped you to understand of the importance of this process. And let me repeat, we have spoken about total internal reflection. And this is also one of those things, as all of the things I'm discussing on this course, that is very important in terms of applications in optics. So tear as a process, as a phenomenon, is essentially the main piece of a physics that we utilize when we make optical fibers, and we want to understand how optical fibers behave, what are waveguides, how they behave, and we can make reflecting prisms, so we can make components such as binoculars, and of course we can also make Fresnel rhombs and other polarization components based on total internal reflection. So this is actually also one of those things that I call good stuff. So now I'm done with this lecture. I thank you for your time and patience during this week. So you have now successfully managed all the lectures that we had for this week. So please congratulate yourself and have a joyful, restful end of the week by just doing the other things that you need to do in your studies. And next week, I will be starting my lectures again, but now I will be speaking about superposition. So essentially I will provide us a kind of starting point on the math that we can then use to understand interference phenomena and such. So that this is what I will be speaking to you next. So thank you for your patience and enjoy the day. Bye bye.